Now let's look at how we can use the output of these sensors to figure out our position in the world. The first one we're going to look at is sensing heading with a gyro. And we talked about heading as the yaw or rotation around the z-axis of some object, of some reference frame. What a gyro gives us is the angular rotation or the angular velocity around one axis. Let's call it the x-axis, right, to get our heading. So it doesn't give us the change in angle, it gives us the velocity of change in angle, so the speed of change in angle. And to get the actual change in angle, to get how far we've turned, we have to integrate the angular velocity over time. So our angular velocity is the change in angle over time, just like the velocity of an object is the change in position over time. So to get the position or get the angle of our system, we have to integrate the angular velocity over time, and that gives us our theta plus some constant, some initial value, right? Now, doing a calculus style integration is really challenging in computers. They're not really happy about doing that. So the shortcut is that we can just do a sum. We take each of the samples of our angular velocity, multiply it by the time that that sample has been expressed. So for basically the time between the last sample and the current sample, and that gives us the change in angle for the last amount of time. Then we just add those all together, and that gives us our total angle. We always have to realize that we're going to be starting from somewhere. So our initial angle, our initial orientation has to be accounted for. An accelerometer works very similarly, except we have to do an extra step. In an accelerometer, it measures the instantaneous acceleration of a reference frame. And acceleration is the change in velocity over time. That's not what we're looking for. We're trying to get position out of this. So we need to integrate our acceleration over time to get our velocity. Then we have to and velocity is the change in position over time. So then we again have to integrate velocity in order to get our change in our absolute position, our actual position, right? Now, again, computers don't like this, so we can convert these integrals straight to sums, basically, right? We multiply our acceleration by the sample time, and add those all together to get our current velocity. Then we multiply our velocity times the sample time and add those all together to get our current position. Now, all of these things together are what we call our inertial measurement equations. And this is what we can use to figure out our position, but it gets way more complicated than this. Because notice that the heading is only one of our angles, and we've got three different angles, and we've only done the x position here, and we've got x, y, and z. And the x, y, and z axis of acceleration also change with our orientation. So if we're moving to a different heading, our position is going to be different in the global reference frame if we've moved in that direction and things like that. So we have to do a lot of math to make this all work, and it gets really complicated in a hurry. To represent all of this information, we can use a lot of different representations. The most common is called the Euler angles, and we'll probably see these a lot. We've got yaw, which is our heading. There's also roll and pitch, and these are what represent the different rotations around the different axes in the moving coordinate system. So there's some things we should be aware of as we're dealing with inertial measurement units and inertial measurement operations. The first thing is that calibration is necessary. All of these sensors experience some kind of internal characteristics, and to get the sort of noise floor, whatever the noise floor is for your environment and the particular sensor and your particular platform, you need to calibrate these things. And we'll have some information on how to calibrate your particular sensor in the next section here. Drift is real and terrible. So the idea here is that every time we make a measurement, there's a tiny little bit of noise in that measurement. We've got noise sources like thermal sources, thermal expansion. We've got noise sources like vibration in the environment, sound, just the wind blowing by, vibration of the earth, a truck driving past on the highway. All of these vibrations can interact with our measurement of our inertial reference frame, and because we're doing a lot of additions of those, we're integrating all of those measurements together, we add them together, even though each one only contributes a small error, that error accumulates. So over time, as you're adding to your measurement, you're also adding error to your measurement, whatever your position and orientation is, and you'll drift a lot. And drift is there, it's real, and it's really hard to get rid of. Figuring out all of this contributes to figuring out your exact position in the world using only an inertial reference frame extremely challenging. The best thing you can do is have a good calibration and try to minimize drift by measuring as fast as you can. The smaller delta t you have, the more you're going to capture of the analog signal that is your motion, and you'll get a better sample rate. You'll get a better overall position and orientation in the world. But there's lots of things you can do to explore this, like dealing with sensor fusion or Kalman filters or simultaneous location and mapping or quaternions or gimbal lock and gimbal gain, the triangulation using radios, temperature sensitivity, star tracking, dead reckoning. All of these things you could spend lots and lots of time working on and learning about in order to be a specialist in this field.